MrCrispin here once again, and welcome to my workshop. I've just got back from America. I've been there on a bit of a musical road trip, and yes, I did take the camera with me and I did collect some footage. Now what I decided to do with that footage is to make a video which I have uploaded to a sub channel. So for those of you who are interested, there'll be a tag at the end of this video where you can find a link to that, or should you be already bored with this video, you can find it in the description now. Back on with today's task, however, and what I'm going to be doing this time is I'm going to be machining a manifold mounting face by means of milling. So it'll be a bit of a study in work holding, hopefully with some information for the beginner and regular practitioner alike. And with all that said, we'll head over to the workbench. Today's component can be seen here. It's made of stainless steel, it's an exhaust manifold, and the task is purely to machine this surface flat by milling. Now the surface does not have to be at any particular angle or position in relation to another piece of geometry. It is purely an exercise in milling this flat. So basically I'm going to set this up in the machine such that this surface sits in line with the machine's axes, and then I'm just going to machine off, taking the minimum material required to regain a fully milled surface. Now the machining should be straightforward, the work holding is the bigger task, and to get this work holding finished in a position where I can actually cut some metal, I'm going to go through several steps, and they are basically: firstly, start at the milling machine and work out, okay, on this milling machine, how am I going to access this and do the machining. Once I've picked those options, I will then consider what tooling could hold the component in that position. And once I've picked the tooling that I've got, I'll then go back to the milling machine and see, okay, is all this going to work? Are the T-slots going to line up? Is there access for the cutter? Is the spindle going to hit something, etc.? So this will be a slightly iterative process where I'll go back and forwards between the machine, the tooling, and consider what the geometry of the component allows. So to kick off this process, let's start at the milling machine. The milling machine I'm using is a Deckel FP1, and I've made the first decision, which is how am I going to actually cut the component. I'm going to do it using an end mill, which will allow me to come in and work around some of these areas. So it's going to be done with an end mill. That leaves me two options. I can either hold the end mill vertically, or I can put it in the horizontal spindle. So in other words, either I hold the component somehow horizontally, or I could set the component up vertically with this face I'm going to machine facing the horizontal spindle. Now it's very tempting to set this up for horizontal milling, actually, because I could come up with some arrangement that clamps down there, giving me lots of long engagement, and then I could put some kind of block in here, pincer it back to the block, and that would be a good solid setup with plenty of access, and that would all work out. However, what I've actually decided to do is to do this with the end mill vertical. It's going to be a little more awkward in terms of accommodating this long face, but I'm going to just use enough of it to do the job, and then I've got a few more options with using jacks from underneath, and as we progress you'll see the benefits of doing it this way around. So I've decided to do this vertically. So the next step of the process is to say, okay, I'm holding this like this. What tooling have I got that will allow me to hold this precisely and rigidly? The first idea I had was to take this adjustable angle plate and then set it up such that this is bolted to the milling table, and then this, by means of manipulating it in different directions, is used to align this with the machine. As you can see, however, there is no holes that match up, unfortunately, so as a plan B I could always drill and tap holes in here to align with the holes I'm trying to hold with, but for now I'll try some other options. So next up was to take this swiveling table and put that something like this to give me 90 degrees, and then I find some kind of block to mount on here. So for example, I could use a few different angle plates, or I could use a block full of holes. But again, nothing has lined up with the whole pattern I'm trying to hold with. So I've explored some other options. Do I put some kind of box plate on there? Almost. But to cut a long story short, what I'm going to do is take this bigger angle block and put this bigger angle block on there. So I can then use T-nuts and studs to bolt the angle plate to the tilting table. And then fortunately the whole pattern here will allow me to run some bolts all the way through. And I can then manipulate this on the milling machine, get everything square. So that's how I'm going to hold it. The next step is to go back to the milling machine and see, does this tooling with its holding requirements fit on the machine table, and are there any issues with spindle access or clamping positions. So it's back to the milling machine, but this time with a much clearer picture of what I'm trying to achieve. Something like this. So potentially, as I come in to machine this, these portions of the machine's spindle could collide with the tooling, so that could always be alleviated by using a bigger, longer cutter. But the bigger problem is actually that the tilting table's fixing places actually overstretch the width of the bed. Now, to cut a long story short, what I have decided to do, because I can't really do much with it, potentially you could put it this way round, but then you're hanging over here and the spindle can't get back that far. So what I've come up with is to use a sort of combination and align the bolts at an angle, something like that. Then I will overhang this slightly off centre, still plenty of strength for what it's doing, something like that, and then I will mount this in here, and then with just a little bit of playing around I will manage to get that, and that sorts out the problem of spindle access as well. So that is how I'm actually going to do this. Then once that's mounted in fresh air like that, I will put a jack underneath and probably some kind of clamp from above. So that is how I'm going to do it. Now it's a little bit awkward setting it all up on here with it being round the back, so what I'm going to do is take all this to the surface table, set it up on the surface table, getting this plane nice and parallel, and then when I bring the whole assembly back over, it should pretty much be preset. Right, well, you'll be pleased to know that I've done the slow bit off camera, which is to find all the suitable nuts, bolts, washers, T-nuts, etc. And now I'm going to try and build this up as an assembly. I made a few felt tip pen marks whilst it was at the milling machine, so I know what to try and replicate. That's going to go on here, so I require a few T-nuts in there. Right, slightly Frankenstein, I know, but that's the nature of these things. And then I'm also just setting the face of the angle plate to be roughly parallel with the face of the tilting table, so that as this tips it does so squarely, which may make the later stages of the setup less infuriating. Right, on to the next stage. Again, I marked and felt it roughly where the component needed to be, and I think I'm going to do 1, 2, 3 and then a fourth down here. To make this a bit easier, I'm going to G-clamp it on. Get something in that region. And now I can make some finer adjustments once I get the bolts in. Okay, so that, ladies and gentlemen, is how I propose to hold the component. All that remains is to actually now align this face to the table, which I shall do with a dial indicator. Right, I'm ready to start clocking, and the idea here is to get this face parallel to this face, and I'm going to check that by using a dial indicator over the top. The end goal here is to get a line along this direction parallel to the table, and then a line along this direction parallel to the table. If those two lines are parallel, then the overall face will be parallel. And to do this, I'm going to be using two different directions of movement. I'm going to be moving the component up and down on the angle plate to control this angle, and I will be using the tilting element of the tilting table to control that angle. Now, to make this as easy as possible, I'm going to try and create a pivot point using these bolts. So I'm going to nip this one up and then have these three slightly less nipped, and that means that then when I come to make adjustments, I'll leave that one loose. When I make adjustments, it should pivot around this top bolt and give me some degree of predictability. So to begin the process, I'm just looking visually, and I can see that this end is a touch low, and the idea of the pivoting bolt is that I can say it's going to move around this point. So if this end is low, I pick this end up, it's going to pivot around there, and this should come higher. That should get me close enough to where I can start actually taking a reading. And I'm not going to concern myself with front to back at this stage. So let's put a reading on there. This is a 10th clock, by the way, 10th of a thou. So 0 all the way around to here, 10, that's 10 thou, or a quarter of a millimetre. So we're still a touch low. Now, because it's pivoting around the middle of this face, as this comes up, this should go down roughly the same amount. So it looks like as I tighten it, it sinks downwards. If I can get that reading roughly 5, that should give me 5 on both sides if the pivoting theory is correct. So not bad. 5 and 5. As you can see, it's only in those two spots that reading is valid, because we've only done one angle so far. So now let's have a look at front to back. So So I've slackened the locking plates that hold the tilting table in position. You do need to be careful when doing things like this, because if it's a particularly free motion, once you take the lock off, depending on how things are balanced, you can get a sudden flop and either trap your finger or damage an implement. So be careful. I do know somebody who lost the end of their finger on a sine table. Okay, so first of all I'm just going to try and get a bit of a measure of how this table responds to treatment. Sometimes they can be a bit stiff and awkward. Let's see then. So if I just give this a nudge, okay, it's pretty responsive. That's fine. So I will begin as before. I'm going to first visually inspect for parallel. Oh, just a side note, before the face pivoted around a line down the middle of the face. So if it was 3 thou low here and I moved it 1.5 thou down here, it would balance out. Whatever you got on one side was happening to the other. Here is a bit more complicated. The pivoting is going on back here, but the 2 points of course are here. So let's say this is low compared to here. As I move this one up, this one also goes up, but by slightly less amount. So slightly more complicated, but I'll get there. Right, so having nipped the table up, I'm now going to take a reading. 0 at the front, 4 thou at the back. So the front needs to go down. Let's see, I'll do this with the end of a hammer handle. Whoops. Six, 4, and you'll see they both readings will change, so they'll catch each other up in a minute. That's 8 and 6.5. With all said and done and everything as leveled out as I can get the slightly undulated face, it is all within approximately 1 thou. So this is now in a position where I can take the whole thing to the milling machine and skim this face. It does look a little old-fashioned. Sorry, no, not me, the work holding arrangements. Okay, feels okay. Let's bring the T-nuts in. Right, work holding arrangement clamped down, and then I've mounted a clock on the machine and checked it, and I'm getting very similar results to what I got on the surface table, so that means I can just carry on. Now, what I said I was going to do was put a jack under here and then a clamp over the top, so that bring the jack up to exactly where it is and then clamp down. However, as I've clocked this up, I found the lowest spot by just under 1 thou is this area here. So I'm actually going to cheat, and because the machining work is going to be very light and the overall requirement is just to produce this surface flat, I'm actually going to allow the jack to push up against the surface and bring the component to 0. So that's put a small load underneath the component and is therefore holding itself down. For the kind of cutting forces involved in this, that's going to be fine, but really for anything more involved, I would want to somehow bring the jack up and then clamp down. But that is going to be a perfectly good machining arrangement for what I'm doing here. And there she stands. That is job done. Now, why did I use such a small cutter? Well, reason number one is to minimise the cutting forces. As you are aware, this is not the world's most rigidly held component, and nice small sharp cutters typically don't put too much force into the workpiece, and therefore the chance of the component wanting to vibrate up and down was minimised. Reason number two is this was all about flatness, and the bigger the cutter, the more the errors in the spindle's alignment manifest themselves over the component. So if you imagine for a given error in the spindle, the bigger the cutter, the more that error shows up in the surface. So equally, the smaller the cutter, the less that effect appears. So that has given me a really nice flat surface. So that is job done, and we will call it a quits at that. So that is that. I now invite you to follow the link to my America video, and apart from that I'll say thank you for watching. I hope you found this interesting and see you on the next video.